Hello and welcome to our unit over atomic structure and nuclear chemistry. In this video, we will take a look at the history behind the discovery of the atom and the major scientists involved. Please come to class prepared and take good notes. The particle theory of matter was supported as early as around 400 BC by Greek philosophers such as Democritus. Democritus theorized that matter is made of tiny, indivisible particles called atoms. And guess what? The word atomos in Greek means indivisible. Unfortunately, his peers, mainly Aristotle, who was extremely influential at the time, did not agree, and Democritus's theories were dismissed for over 2,000 years. So in about the early 1800s came John Dalton, and using actual scientific experiment, this is important, he formulated the first atomic theory, and he came up with 4 points. Number 1, all matter is composed of extremely small particles called atoms. Number 2, all atoms of one element are identical but different from those of any other element. Number 3, atoms of one element combine with atoms of another element to form compounds during chemical reactions, and they combine in simple whole number ratios. Number 4, atoms are indivisible. In addition, they cannot be created or destroyed, just rearranged during reactions. Dalton's theories completely revolutionized scientists' concepts of matter and the atom, and they were supported by actual experimentation. Dalton's theory, however, had 2 major flaws. In point number 2, it states that all atoms of one element are identical. This is not true. Not all atoms of the same element are identical. Isotopes of a given element are not all identical. Isotopes are atoms of the same element that have different masses. Scientists had no way of understanding isotopes at that point in history, and we will learn some more about isotopes later in the unit. Then in point number 4, it states that atoms are indivisible. This is also not true. This piece here is not true. Atoms are divisible because we now know that they are made up of even smaller particles, the protons, neutrons, and electrons. This piece of the theory, however, was true. Atoms cannot be created or destroyed, just rearranged. Around the time of Dalton, scientists had begun to quantitatively experiment with chemical reactions, and they came up with 3 basic laws. One is the law of conservation of mass, which states that matter cannot be created or destroyed during a chemical reaction, and this is supported by Dalton's theory that does state that chemical reactions involve merely the rearrangement of atoms, and during chemical reactions, atoms are not subdivided, created, or destroyed. Then the law of definite proportions, which states that a chemical compound always contains the same proportions of elements by mass. For example, sodium chloride, NaCl, also known as table salt, will always have 39.4% by mass of the element sodium and 60.66% by mass of the element chlorine. Then there's the law of multiple proportions, which states that elements combine with each other in ratios of small whole numbers. If 2 elements form multiple compounds, so for example, if we combine carbon and oxygen, we can form carbon dioxide. We have 1 carbon for 2 oxygens. We could also form carbon monoxide, which has 1 carbon for every 1 oxygen. What we cannot form is CO half, for example, because that would not be a ratio of whole numbers. About 80 years after Dalton came J.J. Thompson in 1887, and he discovered the electron in his experiments with cathode ray tubes. What a cathode ray tube is it's a tube filled with a gas at low pressure, and at one end of the tube over here we have a cathode, which is negatively charged, and an anode, which is positively charged. And we apply a high voltage around these 2 electrodes. And what happens is it produces a beam of particles that flow from the cathode to the anode. So then what Thompson did is he put two deflecting plates around this beam of particles, which is called a cathode ray. So there is a negative plate and a positive deflecting plate. And what he observed was that the cathode ray was always deflected towards the positive plate. So what he concluded from that was that this beam of particles, or cathode ray, was composed of negatively charged particles, which he called corpuscles. These particles later became known as the electrons. Thompson actually tested this with a lot of different gases and also a lot of different metals for the cathode and the anode. And what he found was that it was exactly the same behavior, for that cathode ray was always deflected towards the positive plate for any metal or gas tested. So he concluded that electrons must be present in atoms of all elements. What Thompson developed from his experiments was the Plum Pudding model of the atom. The Plum Pudding is a British cake which has raisins in it. So he compared the raisins to the electrons. Probably a better analogy for us would be a blueberry muffin. But what he said was that there was some negative electrons which were evenly distributed in the atom in a matrix of positive charge or matter around those electrons. After Thompson came Ernest Rutherford, and he is famous for his gold foil experiment, which helped him discover the nucleus of the atom. Rutherford bombarded a very thin sheet of gold foil, imagine a lot thinner than tissue paper, with fast-moving alpha particles. What alpha particles are is they are positively charged helium nuclei. So there is a radioactive sample of matter inside a lead chamber to protect it, and the alpha particles are bombarded towards that thin piece of gold foil. Based on the Plum Pudding model of Thompson, he expected that the mass and charge of the gold atoms would be evenly distributed, so that the alpha particles should go through the gold foil undeflected. But much to his surprise, some alpha particles were actually deflected back completely and bounced back, and some were deflected at large angles. So what he concluded was that the alpha particles must be hitting a very small, dense, positively charged structure with a very large mass. And this structure is what became known as the nucleus. So if we look at this picture here on the right, there's the layer of gold foil, and here are the alpha particles. Most of them are going through undeflected. However, if you are hitting that nucleus and being deflected, and sometimes they are even bouncing back. So the second thing he concluded, because the vast majority of the alpha particles were not undeflected and went straight through, he concluded that the atom must be mostly empty space. So from his gold foil experiment, Rutherford concluded two things. One, the atom contains an extremely small, dense, and massive nucleus, which is positively charged. And secondly, most of the rest of the atom is empty space. Rutherford later discovered the proton, and one of his students, James Chadwick, discovered the neutron, and they found that both the proton and the neutron were found in the nucleus of the atom. A few years later, in 1913, came Niels Bohr. Developed the Bohr model of the atom, and he said that the electrons have to be restricted to specific energies and follow paths called orbits, a fixed distance from the nucleus. So here's the Bohr model over here. It is absolutely not to scale because the nucleus is infinitely smaller than this. but there are the protons and the neutrons inside the nucleus. And he said that the electrons follow fixed paths around the nucleus, and he compared it to the way planets orbit the sun. We now know that electrons actually do not have neat orbits like the planets. However, the Bohr model is an extremely useful representation of the atom, and it's still widely used, although it is not a true representation of how the electrons are distributed around the nucleus. The latest or modern atomic model is the quantum mechanical model. It is the mathematical model. It is the current model of the atom, and it was developed in the 1920s by the work of several scientists, de Broglie, Schrödinger, Pauli, and Heisenberg. We now know that electrons exist in regions of space instead of neat orbits around the nucleus, and these are called orbitals. Notice orbitals is not the same word as orbits. And the paths of the electrons are random and cannot be predicted. We can only talk about the probability of an electron being in a certain region. If you look at the model here, electrons have a higher probability of being located nearer the nucleus, and you can see the blue is denser close to the nucleus, and further away we have less probability of finding nucleus, and you can see it's less dense. This is also referred to as the electron cloud model. So here's a neat summary of the atom, starting with Dalton, going all the way to the quantum mechanical model. It would probably be useful and helpful if you drew the evolution of the models from the time Dalton came up with his atomic theory to the current quantum mechanical model. This concludes today's video. See you in class with your notes and questions.